All right, so we're going to get started here, and we're going to go through the whole process, start to finish, of locating an earthquake epicenter, right down to the map. But for right now, I'm just going to kind of go through this practice exercise really quick, which is in the notes file that I provided for you. And it just gives you a seismogram for one location, and we're just going to go through it for that one location. And then from there, we'll go down and we'll actually do an example where it gets us right to the final map. So I will show you that as we go here. First of all, put your name on here. Otherwise, you'll forget who you are. And then what we're going to do first is basically fill in this chart, which is fairly typical. Obviously, you've got your arrival times for P and S waves, your difference in arrival time, distance to epicenter, which we have to find. And then I'll show you how to get the P wave travel time and the origin time. So we'll do those right now. First step is to correct this chart. First, right there where it says 2300, it's actually 1300, and you'll see that come out actually from our calculations in just a second. And the other thing is down here on the bottom, this is a scale error. I don't know what they were doing there. This is 0200. So anyway, you know, nothing's perfect, nobody's perfect. Just keep that in mind. I'm going to actually write in finer pen here in black. We'll write the actual time. So it's 002. Okay, so that makes, if you look at the whole deal here, each these little tick marks is a different minute. So what you're looking at in times here is the hours. And then this, well, this is the minutes, and these are the seconds. So it's just like a full clock time. Now, what you'll notice though, is that all of the hours are 0. They were doing this to be friendly and make it a little easier on us. So I'll show you what to do about that, because they're all 0 hours. So we can just make some assumptions there and clean up our actual diagram here a little bit. So here's what we're gonna do. We're gonna find the P wave arrival time, and I'm going to pick this spot right there where the P wave first starts to spike up. We're gonna draw a line all the way down to the axis. And I have this straight edge thing that happens automatically here, so that makes it nice and easy and very precise. And so I'm kind of between, if this little tick mark right here is 05 minutes, I'm a little bit shy of it. And so 4 minutes and 30 seconds would be about there. It looks like I'm about 4 minutes and 45 seconds. So I'm going to take 4 minutes and 45 seconds as my P arrival time. So down here, you could write 000445, but obviously that's a lot. And you know, you start doing many of these, it's going to get a little bit cluttered. So I'm just going to do this. You can write it just like this, 445. Keeps it nice and easy. Okay, so we'll do the same for the S wave down here. And I'm going to find that little spike right there where it first starts to go up. And I'm going to go down to the axis. And so there we go. This is 07 right here on that little tick. So I'm a little over 07, about halfway between 7 and 7:30. So that's about 7 minutes, 15 seconds. So again, I'm just kind of estimating. You might get 10 seconds, you might get 20 seconds, a little in either direction. It's okay. I'm just going to go with 15 because I know the answer. So I'm going to write 7:15. Okay. So now difference in arrival time is, we're going to do the subtraction. We're going to do P and S wave difference. And here's the deal. You want to always do the big or the later time first, because that's going to give you a positive answer and things like that. We don't want it to get crazy. So we're just going to do a time subtraction. So you're going to always do for this S wave minus P wave. And so I'll do this over here right underneath. So we're going to do 7:15 minus 4:45. And so this is going to be maybe a throwback to elementary school, because how do you do 15 seconds minus 45 seconds? Well, don't give up. You actually have to, and I'm going to change color here, you actually have to borrow a minute. So make that a 6. And this 15 is going to become 15 seconds. And we borrowed 60 more seconds by taking away that minute. So you're really doing 7, or well, let's do this. Your actual problem is 675 minus 445. So again, this is like time subtraction. You got to follow these rules. And if you're not sure why we just did that, you just have to treat the seconds as a group and the minutes as a group. So 75 minus 45, we've got 0 and 7 through 30 seconds there. And then we've got 6 minus 4 is 2. So the difference in arrival time that we're going to actually go with is 2 minutes, 30 seconds. Now, if you go back up here and actually count that, well, it's this gap right there is 2 minutes and 30 seconds. And it makes sense because you got 15 seconds on one side and 15 seconds on the other side that are kind of extra there. There's your 30 seconds. And then 2 minutes went by. So that's what we're doing for that. Now, to find the distance to the epicenter, this is where you've got to use the chart that I had you download. Hopefully you printed it. There are ways to do this digitally, which you're about to find out, but it doesn't necessarily work as smoothly. So the first thing, what we've got to do is take that 2 minutes and 30 seconds and use this chart to find out the actual distance of that place to the epicenter. And so I've got myself all set up with this Post-it note looking thing, and I've got a little red line on it already, and there's a reason for that. I'm going to bring it down to the axis here. And we're going to put the one corner right on the bottom of the axis, so right there against 0. Now, for you, if you're using your piece of paper, you would just put it anywhere like that. And now watch what we're going to do. We're going to take this little line here, put it on 0. And we want that line to be 2 minutes and 30 seconds, which is right about there. Okay. And I'm going to slide this thing over a little bit, and so you can still see the little tick marks there. Very important. And I'm going to make sure that these little boxes are right there where we want them. So about 2.5 minutes. So you all see that? So there it is. That's a difference of 2 minutes and 30 seconds. I'm going to put it back on the edge of the Post-it note here, and we can move this whole thing together as one unit. And what you want is this little red line to fit, or the gap or the interval that you made. You can just use tick marks. You want it to fit exactly in between your two curves there. And again, it's kind of tough for me to do this. And I actually think that's a little long from what I can tell. Yeah, it's a little bit longer than it should be. So it's going to fit. I'll just decrease the size just a smidge because it was a little too long. It should fit right about there. Okay, so it fits right in between those two curves for P and S wave, right about there. And again, if I left that there, that's probably what I should have done, right? If you follow that down, and I'll use a different color here, use green again. If you follow that down, you're getting right around 1,300 kilometers. And that's the distance of whatever the name of this place is from its epicenter of that earthquake. So it's called Jan Mayen Island. So we just figured out, as it said in the picture in the first place, it's about 1,300 kilometers. Okay, so here's the deal. If you got 1,200, are you wrong? If you got 1,400, are you wrong? No, but there's a best answer as to how these things tend to work out. And you obviously want to try your best to get it there, but it's not going to be the end of the world if you're slightly off. So let me click now. We've got to find P wave travel time. So I'm going to go back to the other thing, and we're going to say, okay. And I can actually leave everything as it was right there. It's locked in at 1,300 kilometers. So when you actually go and find the P wave travel time, you're literally going to go across, I'm going to use blue this time, from wherever you hit your P curve there, right at that bottom point, you're going to go straight across and read the time. And I messed that up, so I'm going to try it one more time. It's a little harder to do digitally than on actual paper, so hopefully you're all using real paper. And so I'm going to grab that little guy and just move it because I know it's a little off. And it's right about there. Okay. So it crosses. Here I am playing around with this digital stuff, and it's just not working very well. There we go. All right, so move it up just a smidge. It's somewhere in between those, in between 2 minutes and 40 seconds and 3 minutes. So it's about 2:45, maybe 2 minutes 50 seconds, something like that. That's how long it took the P wave to get to our little island here. So that's how I do that. I go across and I read the right where the P wave curve kind of crosses your little straight edge piece of paper there. You just run it across, read that time, and that's it. So if you look, the S wave is right up here around 5 minutes. So if you actually wanted to find that time, you could. I didn't ask you to, but there it is. So you kind of just go straight across from that point, and you get around 5 minutes for the S wave. All right. So let's go back over. What did I say it was? 2:45-ish? That sounds about right. Let's go back and pop that into our chart. Switch back to red. So 2:45, right? So when you actually do to get the origin time, that's actually a subtraction. So we want to say, all right, well, it took the P wave 2 minutes and 45 seconds to get to me, which means the earthquake happened 2 minutes and 45 seconds ago. So when did the P wave get to me? Well, it got to me at 4:45, okay? But it took 2 minutes and 45 to get there. So we've just got to do a difference here. If it gets here at 4:45, but it took 2:45 to get here, then what do I get? That means the origin time of this earthquake was 2 minutes. So then 2 minutes and 45 seconds after that, the P wave got to this island, which is where your 4:45 comes in. Luckily, we had to do no minute borrowing here, so that was nice and easy. So it's about 2 minutes for the origin time. So that's that. All right, so that's the full workout for just one station. Obviously, you'll go through this faster than I just did when you start getting the hang of it. All right, so now we're going to go through the actual example together. You can feel free to pause this video at any point as you work these out. And eventually I'm going to work it out too, so you can check your answers kind of as we go. But I'll do Houston right now, and then I'll pause mine and I'll just fill everything in, and it'll resume the video for you. And then you just see all the answers pop up. So Houston, just to do Houston together, because I want you to see how the scale works. Right here, you'll notice they're all 0 hour again, so we don't have to worry about hours. And you've got 10 minutes here, and then this is 11 minutes, 12 minutes, 13. That's going to be important, obviously, 14. So all the little tick marks in between, though, these are 20 seconds each. So if you're looking at where this P wave arrived, this would be 12 minutes, 12 minutes, 20, 12 minutes and 40 seconds, and then right where this guy is 13 minutes or 12 minutes and 60 seconds. So I actually just figured out the answer to my box down below, so I'll go and write that in just a second. S wave while we're here, this is 15, that's right on 16 minutes. So we've got 13 minutes and 16 minutes for our P and S wave. So 13 minutes and 16 minutes. All right, and obviously that leaves us a 3 minute difference. If you just do that in your head, that's an easy one, right? All right, so Chicago's got 15 minutes, and it looks like about 19 minutes right there. So 15 minutes, and then 19. And then we've got a difference there of 4 minutes. Then the last one here is Seattle, and so let's look at that. This is 10, 11, 12 minutes right on the nose. And now this one, this is 14. It looks like 14:20 and 14:40. So 14 minutes, 40 seconds, 14:40. So I'm going to write that before I forget it. And then we said the P wave was 12 minutes. And of course, now we've got to do some subtraction in order to figure out the actual answer here. So, or the difference. I'm just going to do this out so you can see me. So S wave arrived 1440, P wave arrives at 12. We'll do the difference. You get 240. So no borrowing needed. So 2 minutes, 40 seconds. Okay. So then we go over to the other thing, the other chart, which I have to click back to. And we're going to do them using this method. So I'm going to just go ahead and pop those answers in there. And I'll pop in the P-wave travel times and origin times. And we're going to talk about why this is actually a terrible example in just a second. But I'm going to go ahead and pause this for myself. You can feel free to keep on working and pause yours. And I'll be right back with the answer. All right, so the answers have magically appeared. I'm going to talk to you about this really quick. There should be always units on every number ever in science. For times, it's just hours and minutes. We kind of assume that, and we also kind of clean it up by leaving those out, I guess. But here for distance, I mean, we're using kilometers, and I just wanted to draw attention to that, just so you know. You're going to be doing that for the entire process here. So km, 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 but you know, you can always put that in parentheses in the data table. Okay, so now we are going to actually find the epicenter. Now, one other thing to point out before we do that, these are wrong. They should be all the same number. If you have an origin time, like an earthquake happens, it happens at the same clock time, you know, or throughout the whole world, give or take whatever time zone you're in. So unfortunately, this didn't work out, and here's why. This is an old example that was drawn. Somebody drew this all by hand. So it is not perfect data by any stretch. So we're just going to let this go. One of the ways you check yourself typically on how you're doing on these is to check your origin times, and they should all be the same number all the way down or very close to each other within reason. So 8 minutes and 40 seconds is really far off. Nothing we can do about it, so we're just going to move on. But we are going to use our numbers that we just got here. I'm going to box them in. We've got to find the epicenter using our distances for each of the 3 cities. So here we go. My digital version of this is a little clunky, so you're going to have to bear with me as I move stuff around a lot. And so the first thing we're going to do is Houston, and Houston is 1,700 away. You don't have to do this in your actual paper copy, because usually you're going to, and you probably are using a drawing compass for this. So you would just set your drawing compass to the right thing and it'd be fine. But I have to actually do this weird crosshair thing in order to actually make my circles go to the right spot. So I'm just going to kind of do the bullseye there over Houston. And Houston is 1,700 away. So here's why we do this. I need a circle that has a radius of 1,700 kilometers. And 1,700 is right here, according to this scale. And you know, different scales are different things. That's 1,700 right there. So I need my circle to actually be that, well, halfway through the circle needs to be that wide. So that's my radius of my circle is 1,700. All right, so I guess we'll use blue for Houston, since it's the closest one, and we're going to move everything around. So watch this. I actually need to move this crosshair thing to 1,700, and you can kind of do this too if you want with your manual method. So what I need to do is make this circle be that big. Why that? Because that, slow down, that is 1,700 kilometers in radius. So from 0 to where it hits 1,700 is halfway through my circle. Then I can move that circle, and this is where the scrolling and the clumsiness of this whole thing, I got to put my crosshair back over Houston, and what it'll do is it'll allow me to move my circle so that it is centered over Houston, which is what you want. You want it to be right on Houston. So there we go. Make sense? So that's Houston. Houston is done. We got to move to Chicago. This is a huge circle. So let me do this. We'll get this gray line out of the way here. And you're going to have to do this too, because 2,600, if you haven't noticed, that's bigger than your entire scale. So you actually have to extend your scale. Now you can do that with a ruler or whatever. I have the option, because this is digital, of doing a quick selection here, and I can just duplicate that scale and make it as wide as I want. And why do I need to do that? Because like we said, I need a circle that has a radius of 2,600, which here's 2,000. Here, this would be 2,500 right there, and 2,600 is right there. So that's how big half of my circle needs to be. So again, very clumsy and weird, but I'm doing it. Chicago is going to be our green circle here. So let me grab him and bring it up. Very, very clumsy. Okay, there, that worked. Nice. Okay, so I put the edge of the circle on 0, and then I'm going to stretch it until halfway. Whoa, that's a huge circle. And I've got to actually make sure I'm the right size here, because that's the name of the game. So I got to make sure it's right on that line. And I moved it, so I'm making sure we're on 0, and it's got to get a little bigger than that actually. A little bigger, there we go. So that circle is now a radius. If you look at it, I'm going to switch. This distance right here is 2,600 kilometers. So you actually do have to extend your scale sometimes. So if you're doing like a compass, like a drawing compass, you can do that pretty easily by spreading your compass to the as high as the scale goes, which in this case would be 2,000, and then just kind of stretching it 600 more by moving your compass around, or you can just draw some more scale. So it's totally up to you. All right, so that circle is ready to roll, and I've got to center him around Chicago. So first thing I'm going to do, and you don't have to do this because you are probably doing this on paper, is I'm going to get my lines set over Chicago here, my crosshairs, and get Chicago locked in. So that's right there. And right here, there it is. Okay, so now I'm going to move this circle so that it is centered over Chicago. And this is very clumsy because this circle is gigantic. Okay, so if all is correct here, it looks like I just about nailed that. So Chicago is now set. So let's get out of this mode and see. We got Seattle as our last one, and that one's a little easier. So it's only 1,600, so I actually can get rid of this extra scale now. Our last one is 1,600 for Seattle, and that's a red circle. So I'm going to set this crosshair at 1,600 from 0. So 1,600 is right there. And our last circle is a red one for Houston. I'm sorry, Seattle. Okay, so we're going to set that circle up so that it is 1,600 in radius, and there it is. And so when you go and draw these guys, all three of them should intersect at one location, which is the name of the game here. And I've got to move, I know it's roughly right about there. I'm going to move this over Seattle to make sure I'm centered. And we're going to get that circle right on those lines, which is right about there. And that is it. So since I did this digitally, and since it was based off of a pretty terrible hand-drawn seismogram type thing, let me get rid of some of this extra stuff so you can see what we've accomplished here. What we've got is an epicenter location. Now, all three of these circles should intersect at one specific spot. Now, my guess is my Houston circle might be a little small, but it should be right about there. Okay. So it's probably just a smidge too small for whatever reason, me trying to do this and get it right. So you see how what I've done is I've got this little bullseye right there where all three circles kind of intersect. Now in your practice with this, you're going to notice sometimes it is more like what I just had, which is actually it's more of a triangle. So let me just go ahead and trace that out. Let's do, I don't know, pink or something like that. Right in here, that is your epicenter location right there. So if you get a triangle that's pretty small like that, that's good enough. You can assume that the earthquake epicenter is like right in the middle of that. And that's pretty close to what it actually would be. So again, perfection is sometimes a little bit difficult to come by in these things, and that's okay. But in a perfect world, if I had done this perfectly around Houston, we should get a circle that's something like that. And that way you have like an actual bullseye. So there it is. That's how you locate this epicenter. Again, not perfect, but I'm going to kind of blame whoever wrote this little practice seismogram. I did not actually do that. So obviously, if I had done it, it would be perfect, right? Sure. So that's how you locate an earthquake epicenter. And I know it's a little more clunky on digital, and you're using a drawing compass. So hopefully the drawing compass is easier and that you can duplicate this process anytime.